we are introducing ourselves to proofs. Geometry is a lot about proving why something is the shape that it says. So why something is a triangle, why something is parallel, why something is perpendicular, why things are similar, things like that. So it's basically a mathematical way of explaining yourself. So explaining why things are the way they are. So by the end of the lesson, you should be able to express a clear and coherent argument visually and in writing. So types of proofs. There's many different kinds, and I know you probably know how to read, so I'm gonna kind of condense this for you, help you find the important parts. So many different types of proofs. Two common types are what are called two-column proofs and paragraph proofs. So that is our main focus today. Two-column proofs and paragraph proofs. So two-column proofs, those are where you have a mathematical statement on one side, and then on the other side you have a justification. So for this, you need to provide rationale in order to prove something. So for each step, you need to explain why you did that step. All right, you can't just say because I said so or because I know. All right, what law, what theorem, what postulate told you to do that? So, to do this, you start with a two-column table. So start with a two-column table with the mathematical statement in the left column and the justification in the right column. So when you're setting it up, you have mathematical statement on the left and your justification on the right. And we'll go through plenty of examples, but let's say I have the problem that I'm given is 2 plus 2. All right, first is usually what you're given. What does 2 plus 2 become? It becomes 4. All right, and maybe the justification for how you were able to condense that into 4, maybe your justification is combine like terms. All right, that's a really short example. Oops, I need to cross that out, but it's just showing you how like usually numbers and symbols will be on the left side and sentences will be on the right side. Questions about that? All right. So the next page is an example for, say, like you're getting ready in the morning. So like a real world example to show you proofs. All right, let's say you have to get out of bed every day at 6 a.m. to prepare yourself to leave for school. Would you think about every step you took from the time your alarm clock goes off until the time you leave your house? All right, normally, no, you don't think about every single step that you do because you probably have the same routine. So you don't really think about what you're doing. Just like when you're in math, when you're simply solving for X, you're not really thinking about every single step that you need to do in order to solve for X. You just kind of know that I have to isolate the variable, or I have to divide this number to get that thing by itself. So in geometry, you're probably not thinking about like the rules necessarily for how to solve something. So like yesterday, we talked a lot about like parallel and perpendicular lines. You may not be thinking that all the time in order to find a line that's parallel to something, that you need to have the same slope. All right, you probably just know that by heart, but you're probably not thinking about the why. So a proof, this is the part you would highlight. A proof is a series of steps with justifications that verifies a theorem or relationship exists. So we're going to create a 2-column proof for your routine when you're getting out of bed at 6 a.m., right, and getting ready to go to school. Getting out of bed at 6 a.m. would be your starting point or your given information. So your starting point / given information is the first thing that you're looking at. And for this example, leaving your house at the correct time is what you're trying to prove, or the conclusion. In a 2-column proof, you're going to write statements in the left column, and reason why these statements are true in the right column. Again, you need the why to officially prove something. All right, any questions so far? So kind of just highlighting important points. I know there's a lot of words there. Okay, so the why must be provided to officially prove something. Headphones away. All right, so here's a broken down example of like a real world example of like getting out of bed. All right, and getting ready for school. Obviously in math you would have more like equations, more stuff on the left side, but this is just like a really simple example. So getting out of bed is what you're given. Usually for the reason or justification, the first one is almost always given. All right, it's the problem that you're told to solve. And then you're going step by step. So like on the left side, you get out of bed, you walk to the bathroom to brush your teeth, then you take a shower, then you dry off, then you put on clothes, right? That's the correct order that they go in. Well, in math, it would be the correct steps that you do the operation, right? And eventually it leads to you leaving. And the reason, obviously this one's more like a silly example, but like, why do you walk to the bathroom to brush your teeth? Right, because you don't want to leave the house with stinky breath. Why do you take a shower? Right, because if you don't, then you'll smell. All right, so reasons on the right side, statements, the steps on the left side. Questions about that? So they'll be structured similarly. Obviously, the left will be more numbers and symbols, and the reason will be the theorems or postulates or rules, whatever. All right, so next page. Then you have what are called paragraph proofs. And you will have to start with a 2-column proof first for these. So paragraph proofs are like a story version, like complete sentences, what you did. So it explains the rationale for each step with complete sentences in paragraph form. And then organize your thoughts first using a 2-column proof. Always do that first. All right, you don't want it to be out of order. So you would take the information from the 2-column proof and begin to develop it in a paragraph proof. So if I use like the storybook example, not storybook example, the getting ready in the morning example, here's what it would be, right? Complete sentences in paragraph form. And you would keep going until all of your statements have reasons for them. Questions about that? All right. So then, now we have a real example, and we're going to use algebra to show it. All right, because we don't know technically a whole lot in geometry right now, other than the vocab we went over yesterday. So we're going to do it with an algebra example. All right, so here's an algebraic problem that we can use a two-column proof for. So here's the first step, or not the first step, here's what I'm given. All right, so like I said, usually the first justification or reason that you have to put in is given to you. So on the left are your math statements. On the right is your justification or reason. So usually what you are given is the justification for that is going to be given. The next thing you're going to need to do, you're going to have to think back to algebra. What the first step normally is to simplify this. What do you think it would be? What did you say? I wouldn't say combining like terms is first. Think about these numbers outside the parentheses. What do I have to do with them? Distribute. Good. So I'm going to distribute the outside numbers from the parentheses to all of the inside numbers. And I have two things I need to distribute. I'll do them in the same step. All right, but once I distribute them, so multiply the outside number by everything inside. What is 4 times x cubed? It'd be 4x cubed. 4 times negative 5x. Negative 20x. 4 times 2. Good. And then distribute that negative 3. Sorry. All right, don't forget to distribute the sign in front of the 3. So negative 3 times 3x squared is negative 9x squared. Negative 3 times 4x is negative 12x, and negative 3 times negative 1 is positive 3. All right, the sign does matter. So make sure you're distributing the sign that's directly in front of each term. All right, so this is what I get after distributing. What would we put in this column for the justification? Good. I would put the distributive property. So the y for the reason we ended up here. This is the y. We did the distributive property to get what we have on the left. Make sense? So what would we do next on the left? Or is this already simplified? So think of your life terms. Are there any other x cubed numbers? Any other numbers with an x cubed? All right, no. And I'll kind of try to keep it with the higher exponents first. Are there any other numbers within x squared? No, so I'm gonna copy that over. Are there any other numbers within x next to it? Yes, I have a negative 20x and a negative 12x. I can combine those because that would be simplifying, is combining your like terms. So what's a negative 20x and negative 12x combined to? You can use a calculator. Negative 32x. All right, combine them and get negative 32x. Are there any other single numbers that I can combine with this 8? The 3, right? So what's 8 plus 3? And it's a positive 11, so we'll put plus 11. So we got to here. What did we do? So what will we put in this justification column? We combine like terms. All right, because that's a rule, right? You can't have, or let me backtrack. This wouldn't be simplified because you have terms that can be combined. So if the quiz was on simplifying things, then this would be incorrect, or this would be incorrect because it's not simplified all the way. So the reason we did this is to combine like terms. Is there anything else that I can do to the left side to make it simplified? Right, you should be thinking no to yourself. So nothing more that I can simplify on the left side, so I am finished. All right, so that's the end of my proof. Questions about that? All right. If I were to make a paragraph proof of this, and let me kind of type this out because that would take a long time to write. I would just be simply explaining what I did and using complete sentences when I did that. So I would say the expression 4x cubed, or sorry, 4 parentheses x cubed, blah, blah, blah. Right, I would type in or write out the expression that I was given. All right, just like that. Then I would say we use the distributive property, or we distributed the 4 to the first set of parentheses. And the -3 to the second set of parentheses. To get 4x cubed minus 20x plus 8 and so on, right? And I would keep going until I got to that very last step. And then I would say, after combining like terms, we get this expression, and that is fully simplified, right? So any questions about how we did that? All right, so you guys will be trying to create your own proofs yourself. So you will be making paragraph proofs, but in order to make a paragraph proof, you need to create a 2-column proof first. So you have practice 1 and practice 2. If you have trouble with like the algebra of it, I can definitely help you. And then once you finish those 2 examples, you will turn them into the basket back here and they'll be graded. All right, so we'll give you 15 minutes to get that done. To create 2 paragraph proofs for each example in your guided notes. Any confusion on what we're doing? All right, so for the practice 2, practice 1 is really similar to the one we just did. So you can look at those steps that we did together. The practice 2 given is this first one, right? So that's what we're given. And you are going to want to first check each side of the equal sign if you can simplify it anymore. On the left side, you cannot simplify it anymore. There's no like terms there. What about on the right side? Are there any like terms? The x and the negative 2x. So remember that like terms have the same variables to the same exponent. So x minus 2x, that's like having 1 minus 2 gives me negative 1x. The 5, there's no other single numbers on the right side, so it just stays plus 5. So now that each side of the equal sign is simplified, you can start moving the variable to one side. You can move it to the right, you can move it to the left. I usually like to get rid of whatever one is smaller. So if I want the negative 1x to cancel, what would I do? You would add 1x, right? That's how I get it to equal 0 on the right side. Then whatever I do on one side, I have to do to the other. Now what I'm writing in red is normally not what you would put in your mathematical statement. So I wouldn't copy the what's in red, just showing you like that's why you did it. So on the left side, we have 4x plus 1x, which is 5x. On the right side, that cancels out to 0, so I just have the 5. Now we want to isolate the x. So to do that, you're going to undo what's being done and always start with what's farthest away from the x. So would I get rid of the 5 or the 3 first? The 3, because the 5 is right next to the x, the 3 is separated by this plus sign. So to cancel out the 3, do the opposite of adding 3, which is subtracting 3. So do that on one side, you have to do it on the other side too. We did it on the left side so that it cancels out. On the left side, I just have 5x. On the right side, I have 5 minus 3, which is 2. All right, almost finished. So what would be opposite of multiplying by 5? So I would divide each side by 5, because you have to do the opposite of what's being done. So on the left side, 5 divided by 5 is 1, which is the same thing as writing this x. And then on the right side, you can leave that as a fraction. And now that this over here matches what we're supposed to prove, then we're done. All right, so you guys will just have to provide the justification. So give me reasons. If you're not sure like what the properties are, I'll kind of be lenient on that. We'll go over what the properties are probably tomorrow when I get back to you. But if you can just explain to me, like we're doing the opposite of what's being done. We need to isolate the x. All right, so I'll give you like, well, if you're finished, you've already turned it in. I'll give you some time to have a break. If you're not finished, just kind of wrap it up and then you can go on break as well. We'll resume at 12:30. All right, so if you already turned it in, go ahead and go on break. All right, so to kind of introduce you to this section, think of this real life situation of a caterpillar transforming into a butterfly. So when it transforms into a butterfly, its body shortens, it grows wings, dull colors become vibrant. So that's like a real world example of something transforming. But in math, when we are talking about transformations, we're talking about a figure, so maybe a triangle, maybe a square, maybe a rectangle. In math, we're talking about its size, orientation, or location changing. So maybe it moves to the left, maybe it moves up, down, maybe it got 2 times bigger. All right, so that would be a transformation in math. It is also sometimes called rigid motion, so I'll highlight that part. All right, but usually the shape is changing in some way. For transformations, you will usually see that there's going to be like the original and then the transformed one. And to kind of indicate that, we map it out on the figure. So mapping is indicated with an arrow. So if our pre-image is for the triangle ABC, then the transformed image is going to be what's called A prime, B prime, and C prime. All right, so A prime, B prime, and C prime. And use this kind of as your guide. So the regular ones will be your original images. The ones with the little dash next to it or apostrophe are called like A prime, B prime, C prime. Those are the transformed ones. So the image will usually have the same letters, but with a tick mark in the top right corner. And then there are 4 different types of transformations. I would highlight those. We have translations, reflections, rotations, and dilations. But today we will only talk about translation. Questions so far? All right, so what is a translation? A translation is when you move something from one location to the other. All right, it does not involve changing the size. It just involves, say, like picking up that purple triangle and moving it to where the blue triangle is. So for highlighting, I would highlight without a change in shape, size, orientation. The side lengths and the angle measures are going to be identical from the original to the transformed image. So like those triangles are congruent, meaning they're exactly the same. All we did was translate it or move it. All right, so taking an object and moving it to a different location without changing its shape or size. All right. Kind of highlight those important parts. Move on to the next page. All right. So when a figure is translated, all points along each segment are translated. So a point line on AB in the pre-image will lie on A prime, B prime in the image. So let's say I have, this is my kind of rough sketch. Here's my triangle ABC. If I translated the triangle on a coordinate plane, it would look something like this. So if I had maybe point W on this line, then I would have W prime on the next line. All right. So preserves all the collinearity, meaning like all the points that were on the pre-image will be there on the translated image. So if there's a line of symmetry in the first image, so a line going down the middle for axis of symmetry, there will be an axis of symmetry in the translated image. All right, so the only thing I would highlight here that kind of sums everything up would be this part. If points are collinear, meaning they lie on the same line, and one point lies between two others, it will be true in the translated image. Right. So next page. Transformations as functions. So you may or may not remember functions, but functions I kind of like to think of as rules. So like function tables, I kind of think of them as having a rule to them. So you can kind of think of it as a transformation as well. And basically what this slide is saying is that functions have a specific rule to them. So if I'm translating A, so maybe my first A coordinate was 0, 0, and it becomes 2, 2. That means I'm adding 2 to the X value and the Y value. So if my coordinate for B is, let's say, 7, 9, it would follow the same rule. I would add 2 to my X value, make it 9, and then I would add 2 to my Y value, make it 11. So they're all changing by the same amount, right? That's what we mean by it being a function. So if my C coordinates, and I'm just making these coordinates up. If my C coordinate was 2, 5, and it has to follow the same rule as what we did before, what would be my new coordinate? 4, 7, right? It follows the same rule. You add 2 to the X, get 4, add 2 to the Y, you get 7. All right, and then these would be labeled with that little tick mark next to it to show that it was translated. Make sense? So while you are copying that example, I'll read out the next example out loud, which is directly under that slide. And it talks about a frog starting out at point 0, 0 on a coordinate grid, and then hopping 3 spaces to the right and 2 spaces up. If you're still copying, just kind of wrap it up, and then I'll go to the next slide. All right, so I read just the first line, so here's the picture that goes along with that. The frog hops 3 spaces to the right and 2 spaces up. So it goes to the right 1, 2, 3, goes up 2 spaces, it ends up right here. This can be represented by a rule. So because it translated 3 to the right and 2 up, we can write it like this. We can write x plus 3 because that's the left or right movement. And then we can write it comma y plus 2. So it looks like a coordinate, except like there's that rule attached to it. If we were looking at the previous example we did on the previous slides, I'm going to go back to it for a second. If I needed to write the rule for this, I would say x plus 2 comma y plus 2, right? Because that's what we did to each x value is at 2. That's what we did to each y value at 2. All right. So with this situation, move to the right 3, up 2, so that's why it looks like this. And if you were having to come up with how it translated or what the new coordinate would be based on just the rule, all you would have to do is plug in the coordinate. So if I plug in my original coordinate, so the frog started at what coordinate? All right, it started at 0, 0. So if I wanted to figure out what the new coordinate is, and on this one, it's probably really easy just to count it. But if I wanted to figure out what the new coordinate would be, just plug in 0 for the x. So we have 0 plus 3. And 0 for the y. So we have 0 plus 2. All right, simplify it. You get that your new coordinate is 3, 2. All right, I know that one was a really easy example, but that's just how we're starting out. All right, keep in mind the pluses right here are only there because we moved in like a positive direction. So if I moved to the left, I would have had to subtract. Or if I moved down, I would have had to subtract. So just keep that in mind. It's not always going to be plus. All right, next vocab word is something called vectors. So going to the next page. We have vector AB with an initial point at A, -4, -3, and terminal point at B, 2, 4. Transformations can be written using vectors. So let's highlight that important part. A vector represents not only the magnitude or length of an object, but also its direction. So they're used to describe objects in motion. All right, the symbol for vectors will look like this, with like an arrow pointing in one direction infinitely. And that is read as vector AB. All right, they kind of look like rays, but their meaning is different. So you'll kind of want to illustrate that in case maybe it asks you the difference between a vector and an array. Array has one endpoint from which it extends in one direction into infinity, whereas vectors have a fixed length. So the vector begins at point A, also called the initial point. And it's indicated by this little tail of the vector. And point B would be your terminal point. So it doesn't go on infinitely. It does end at the terminal. So B would be your terminal point. It's just showing you the direction that is going from A to B. Questions about that? So that would be a good quiz question, is the difference between a vector and an array. All right, so now we are going to look at 3 sets of figures. All of them are translated. It's just some of them have movement in one direction, some of them have movement in 2 directions. So over here, starting with figure 1, we have it where this is the rule. All right, and we're going to highlight the rule for this first one. So notice, is there any movement left or right from this top hexagon to the bottom hexagon? Does it move left or right at all? That is why the rule for it is just x. All right, I guess you could write x plus 0, but x plus 0 is still just x. So that's why it is x, comma, y minus 3, because it's going down. So since the y values are changing by 3, so it's going down 1, 2, 3 from D to D prime, that's the rule that we're following. Make sense? So if I was just given the first shape and I needed to draw the second one, that's what you'll have to do on your practice, is you would just take each point, the x value doesn't change, but the y value moves down by 3. All right, now look at figure 2. And I know the rule is somewhere down there, but I'm not going to look at it. For this one, is there any movement from the left to the right? Yes, there is. First, which way is it going? Is it this one translating to that one, or is it this one translating to this one? All right, it's going from left to right. You know that because it has arrows, but usually those arrows won't be there. If you didn't know, the prime tells you that that's your translated image. All right, so anytime you see the prime, that's your translated image. How much is each point moving to the right? All right, it's moving to the right, 1, 2, 3, 4, 5, good. And since it's moving in a positive direction, we write +5. And I just kind of focus on points that are labeled the same to keep that going. All right, what would be added to the y value? Anything? Is there any up or downward movement? All right, since there's no up or downward movement, we're done with that rule. All right, because it would be y plus 0, which is just y. So no up or down movement, the y stays the same. Questions? All right, now we have movement in both directions, right? So we have up and down movement and left or right movement. So just focus on your original image and maybe start with the x's. How much to the right did E move? All right, it moves 3. And did it move in a positive direction or a negative direction? Should be positive for the left to right. Does that make sense? When we go to the right on the number line, numbers get bigger. So x plus 3. Now do the rule for the y value. How much down did that e move? It moved 3. And did it move in a positive or a negative direction? All right, that's our negative direction. So going down, the numbers get smaller, so it should be minus 3. Questions about that? All right, so notice, like, let's look at point F. The coordinate of point F is -3, +3. And to get to F prime down here, we are adding 3 to x, which makes x 0, and subtracting 3 from y, which makes the y 0. All right, and it is at 0, 0. Questions? All right, so then, be here for just a second. All right. So first example, we have the hexagon titled waters, all right, because it's labeled WARS, shown on this coordinate plane, and it's translated according to this rule. All right, so the rule is given to you, you have to follow it. You will have to graph the hexagon, basically waters prime, W prime, A prime, T prime, and all of that. All right, so when it's on a grid, you could probably just count, go down or to the left 4 and down 7 for all of them, since this is negative movement. Or you can identify each point and subtract from each of those. Since most of you are probably more right-brained, you're probably better visual learners, I would say counting might be easier. So the -4 means we're moving in what direction? So we're going to move left 4 on all of these, and we're going to move up or down 7 for the y. All right, good, because that is negative movement. So we're going down 7. All right, try it out on your own paper. I'll do W and then try out the rest on your own. So we're going to the left 4. 2, 3, 4, down 7. So then W prime should be down here at -1, -2. All right, but the rest of them on your own using the same. If you move each point according to the rule, then you should have the following. So moving left 4, down 7 gives you A prime. Right, and then from there you can probably kind of come up with the rest on your own. But then going left 4 on T and down 7. Left 4 on E, down 7. All right, and the images should look exactly the same The side length should be the same. The angle measure should be the same. And then what you get is your translated image. Should look something like this. All right, questions, comments? All right, we'll do one more together and then you have some to try on your own before doing the practice. All right, Nicholas, figure it out. Nicholas. Wake up. I have to talk to you again. All right, so we have triangle CAT is translated on the coordinate plane to C prime, A prime, T prime. If we have the following height, which is titled lion, so Lion, and translated to the same rule, we need to draw where the new one would be. So first you need to figure out what the rule is for the first translation. So going from C to C prime, how much did you move to the right? 1, 2, good. And would that be your X value that's changing or your Y value that's changing? All right, X plus 2. All right, and it's going in a positive direction. The numbers get bigger when you go to the right. So that's why it's X plus 2 for the rule. What about the movement up or down? What was the movement up or down? From C to C prime. Moved 3 spaces, and since I'm going upward, is that positive or negative? All right, so this is the rule. You can confirm it with the other points if you like. You can test out A to A prime, T to T prime, but you'll see that you're moving to the right 2 and up 3. So since this is the rule that we need to follow, because it says that the lion shape follows the same rule, graph the translated image. So for each X value, you should have movement to the right 2, going up 3. And then make sure you label it prime to show that it's translated image. Right, up 2 to the right 3. All right, anyone confused where we're getting these numbers from? All right, it should look something like that. All right, and this one doesn't just ask you to draw it, it asks you to identify the coordinates of each one. So you could just make a list. L primed, I primed, O primed, and N primed, and identify the coordinates of each one. All right, if you're not good at identifying coordinates, then you need to practice. So what is the coordinate for L prime? The XY value for L prime. 0,5, good. If you start at the x-axis, that number is 0, at the y-axis, 5. What's I prime? What coordinate? 3, 7. O prime is what coordinate? I read it as 6, 4. Let me check my paper. Oh wait, it is 5, 5. I guess I just put it wrong on the screen. All right, but it is 5, 5. And then M primed is what? 3, 3. All right, good. Any questions? All right, so then you have a few examples. I'll leave this one up, but you have the U tries for page 6 and page 7. So you have 3 examples to try on your own. I'll project those answers in about 5 minutes. And then you will use 15 minutes after that to complete your assignment. All right, so did you try problems in your guided notes?